Hi, Adam.
Hey, how you doing?
All right. How you going?
Pretty good. Just, brewing some coffee right now.
Okay. Fair enough.
All right. I got my new monitor today. I'm gonna wait until like 6 o'clock to unbox it. So,
All right. Well, fair enough. Just know we're
how
being
are you doing
just
today?
just know we're being recorded, Adam. So
No, I know.
just letting you know. All right.
Yeah, that's why I put the hat on because head looks crazy.
Fair enough. All right. There's Miriam. Hi, Miriam.
Hello, Professor.
We'll get started in a couple of minutes or a minute and a half or so. All right, folks. We'll get started here, and we'll start on test 3. What you're going to see here. I did send out an email last night reminding you of some certain facts about test 3. One of those is that you'll have test 3, which is actually 70%. And then there's also this test 3 units quiz as well, that's worth 10%. Now you have unlimited opportunities at this units quiz. I'll just give you an idea what it looks like. And because I can't really get you to show your work in some of those quizzes, the way I've got this set up is so that you can show your knowledge of dimensional analysis by doing this kind of matching exercise here and assigning units or units and numbers to these various numbers here, 1 through 5, and the unused answer. Now, there's a bit of a trick to these matching exercises in my courses. And what you'll find is that there's a video here. Let me see if I can go back to it. There's a video here that I've included, how to do matching problems in my courses. And you have to make sure that you include that unused answer as your answer. You can't just ignore those. So you'll see that. I'd recommend you you watch that video, make sure you see what you're doing first before you do this units quiz here. Like I said, you can take it unlimited times. It's not done under on a lock, so you can just go ahead and do it as many times as you need to understand what you're doing. All right. The other thing is that for 20% there's the essay questions here. Now sometimes people wonder, well, why are you doing this? Why are you even having these essay questions? Well, the reason is because they are part of the curriculum, but they're not things that really need to be, or shall we say, taught. I mean, if you can just read about them, but they are pretty interesting. I think they are anyway. I think a lot of people end up getting more out of it than they think they're going to. So these are the topics that I want you to do, and what you'll do is you'll do them on a sheet of paper. You'll do them or on multiple sheets of paper if need be. And it's going to be 50 words for each essay, and each essay needs to include a reaction that relates to what you wrote in the essay. Now, all of these are redox type processes, oxidation reduction type processes that you're looking at here. And what I'm expecting to see is the half reactions and the full reaction that relates to that topic. Now, millions and millions of words have been written about all of these topics all across the internet. You might even find some stuff in a textbook if you've got a textbook. You can just look up in the index. I don't care where you get the information from. The whole point of this is to let me know that you've read and understood something about these particular topics. That's the only point. You see, the thing is, I could assign this as reading, but while people might have great intentions about reading about these topics, I can't guarantee that anybody would unless I actually assign something for a grade. And that's what I'm doing here. So it's not particularly difficult. I do often get inquiries about what I'm looking for. Well, I think I'm being fairly clear about what I'm looking for here. But if anybody has any questions about what I'm looking for, please feel free to ask right now. Does anybody have anything that they'd like to ask about this essay question? Or essay questions, as I've got them here. Now, the way I would usually handle this is in a regular test, I have actual essay questions and I allow students to bring in a sheet of paper to write these essays. But that's not really able to be done here. So what I do is I have you do the essays and then hand them in to me. Just make sure that you understand that they need to be handwritten and they can't be photocopied. And you're going to sign across the document as well.
And also, it seems like we can turn these in prior to taking the test at any time?
You can turn them in any time you like, Rebecca.
Okay.
Yeah, and I'll grade them straight away. And I recommend getting them done sooner rather than later.
I did notice that in your notes, and I just wanted to be clear that we could do it separately, like not do them ahead of time, but have to wait to turn them in.
Right, absolutely.
Okay.
Yeah. I'll grade them straight away too, obviously.
Okay.
But, the thing is, there's a lot of latitude here. There's a lot of latitude. As long as you can write about anything, as long as it relates to those specific process you choose. You could talk about uses. You could talk about the reaction itself. You could talk about how a dry cell battery is made, or anything like that. As long as it relates to those reactions, I'll be happy with that. Remember, the whole point is for me to know that you've looked at it. You've learned something from it. That's all. All right. Any other questions about the essay questions here?
I mean, we're going to learn all of this stuff next chapter with voltaic acid.
Well, with the redox equations and the voltaic cells, yeah.
Okay.
Now, today, I'll do a little bit of that, but my main focus will be on thermodynamics today. All right, so let's take a look at, we'll take a look at the test here. All right, so this is the paper test, and as I said, these practice tests and the test you'll actually be taking are based around questions that relate to these kinds of questions that you see here. So this specific question is about this reaction And I'm hoping that you've done some looking at some of the videos here. So I'm not really going to go into the nuts and bolts of it. I just want to go into how we do these kinds of problems here and how we handle thermodynamic processes. So there's two equations that we deal with here, one for delta H and one for delta S. Now, delta H is heat of reaction and delta S is entropy. And then we also have this other thing called delta G, which is a combination of delta H and delta S. Now, what we find, and this is just as in general, we find that reactions that release heat and reactions that increase in entropy tend to be favored over reactions that are the other way around. And that's why we have this delta G here that will allow us to determine how favorable it is. Also, the sign of delta G is important. If it's a positive value, then it's not particularly favorable. And if it is a negative value, then it's much more favorable. Now, I'll get into more of that when we look at question 2. But as far as question 1 goes, all this is about is calculating this value of delta G and this value of K. Now, K is something we're already familiar with. It's the equilibrium constant. It's a measure of how favorable or unfavorable a reaction is, because we can get an idea of, let me pull up my screen here. I'll do a little bit of explanation about K. So let's say you've got this reaction where A goes to B. K is going to be the concentration of B over the concentration of A. And you can see that the bigger the value of K, it means there's more product. That's really all we're saying. And there is a link between delta G, which is a measure of how favorable a reaction is, which means how much product it's getting, and this value of K that we talk about here. We've already dealt a lot with the equilibrium constant. Does anybody have any questions about background for this that they'd like answered? Specific questions? All right, well, let's get into the kinds of questions we need to be cognizant of here. We're given these delta H values, delta H of formation specifically. We're also given entropy values for these individual substances that are part of this reaction. When we look at tables that contain these values, you'll often see things like NH3 gas, you'll see NH3 aqueous, and it's important when we're looking at a reaction to make sure we're cognizant of the state of what we're looking at, because as you can see, the heats of formation of these things is going to change depending upon the state that it happens to be in. And some of these are relevant and some of these aren't. So that's important when you're looking through the tables. And that's important, of course, when you're doing the extra credit stuff, where you have to look at the tables. In the questions you'll be answering, it won't be so important, because I give you the values without too many red herrings like I do here in this question. If we're looking for the heat of reaction, what we're calling delta H, it's going to be the sum of the heats of formations of the products minus the sum of the heats of formations of the reactants. So the actual equation here for delta H is this sigma delta HF naught products minus the sum of the heats formations of the reactants. So the heat of formations are the heats of formations themselves. So let's say we had the heat of formation of CO2 gas. The heat of formation, in a nutshell, is really just the energy tied up in these bonds. That's all we're looking at here. The definition of heat of formation is the heat released or gained when this is made from elements in their natural state. And that's going to be a link to its stability, and therefore the stability of each of these plays into the heat that's released during a reaction. So in this specific case, I can tell you that the delta H is negative 8.4 kilojoules per mole, which means that the products are 8.4 kilojoules more stable than the reactants overall. When we take into account bond energies and everything else, that's what we can say. The reason I say that the products are more stable is because of this sign, this negative sign, which indicates that the reaction is exothermic, which means that the energy profile looks something like this, meaning the products are lower energy than the reactants. So we'll have energy here, we'll have reaction pathway here. So as we go from the reactants to the products, we find the products are lower energy than the reactants, to the tune of 8.4 kilojoules per mole. And that's what that delta H value there is. It's that difference in energy between the products and reactants. So the way we do that is just simple math. We identify, first of all, which things we're dealing with. We're NH3 gas, we've got H2O2 liquid, we've got N2H4 liquid, and we've got H2O liquid. And you can see what the student's done here is crossed out anything that's irrelevant, which I think is smart. And then they've done some simple math, added up everything that's on the product side. And when you do that, you'll see that it's 95.4 kilojoules per mole. That's for the N2H4 liquid. And then it's 2 times the H2O liquid because there's 2 moles of H2O here. And then that allows us to come up with the total on the product side. And then we subtract everything on the reactant side as well. Now this looks like it could be a multiplication process, but it actually isn't. This 2 times here is the result of this counting number, which means it's really this plus this. So this whole thing is addition subtraction, which means that in order to figure out the number of significant figures, we look at the smallest number of places past the decimal point. And you can see that's going to be 1 place past the decimal point, which is why we end up with negative 8.4. And that does have the correct number of significant figures. Does anybody have any questions about the delta H naught calculation? You're all fine with that? And the sig figs? Okay. The delta S, sorry, go on, Adam. Sorry.
I'm sorry, I actually do have a question.
Mm-hmm.
So whenever we're setting this entire problem up, what is our main focus? Just whatever is on the products and then minus the reactants?
Mm-hmm. That's
Okay.
right. And that's just to get the delta H value. And then we're going to get the delta S value. Now, the reason we're doing that is so we can get the delta G value, which is a combination of delta H and delta S. So we'll use those values in a second. Now, the delta S is a measure of entropy. And what it is, it's a measure of disorder. And what we know is that the universe is always tending towards a greater state of disorder. And disorder is really about probabilities. So if you've got a room that's clean, it means there's a place for everything and everything's in its place. But unfortunately, what we know is that there's far more combinations that allow for your room to be what you would call messy. There's a million different ways that everything could be arranged and have your room be considered messy, but only one way that your room could be arranged and have it considered to be clean. So there's far more probability it's going to be messy than it's going to be clean. And that's all we're talking about here when we're talking about disorder. I'll go into more of that in the next question, how we can actually look at a reaction and tell how much order there is on each side. But in this instance, it turns out that there is more order on the on the product side than the reactant side. And I know that because this value here is negative. So delta S is products minus reactants. So you can say it's the disorder on the product side minus the disorder on the reactant side. But since there is more disorder on the reactant side, it turns out that we get a negative value here. Now, if you take a look at the actual process, you'll see that we have liquid, liquid. So we have 3 molecules of liquid over here. And over here, we have 2 molecules of gas and 1 molecule of liquid. Gases are far more disordered than liquids are. There's far more ways to arrange gases than there are liquids. So we find there's a whole lot more disorder on this side than this side. That's why I know that we're getting a negative value here. But that's just a consequence of doing the math here. And it turns out that this one with the smallest number of places past the decimal is this one. So there's no places past the decimal, and that's why we get negative 224. And the unit here is joules per Kelvin per mole. The units are up here.
Mhm.
Does anybody have any questions about entropy? If you want more information, you can watch the video about it. But does anybody have any other questions about delta S? So once we've got delta H and delta S, we can go ahead and we can calculate delta G. Delta G is delta H minus T delta S. But you'll notice that the unit for delta H is kilojoules per mole, while the delta S unit is joules per Kelvin per mole. This produces a situation where we're comparing apples to oranges. And we really do need the same number, the same joule unit or kilojoule unit in order to make this work. So what we do here is we have our delta H, which we get from up here, minus 8.4 kilojoules per mole, minus, and this is T delta S. Now T is the Kelvin temperature, so it's 25 degrees Celsius, and that becomes 298 K. Now when we're doing the temperature conversion, I just want to point this out, because it's not been shown here. It's going to be 25 plus 273.15 K, which comes out to be 298 K. You'll notice that this has no places past the decimal. This has 2 places past the decimal. So this has no places past the decimal. Bottom line is it doesn't matter if you use 273 or 273.15. You're going to get the same result if you plug 25 degrees Celsius into that equation. Does anybody have any questions? All right, so we got T delta S, and you'll notice we got T times the delta S value, but that's joules. So what we do is we multiply that by 1 kilojoule over 1,000 joules, and that will convert the joules into kilojoules. And then we can be in a position where we can subtract the kilojoules per mole and kilojoules per mole, which is how we get this answer over here. As far as sig fig goes, sig figs go, this is going to always be 3 sig figs because the temperature is 3 sig figs. And then the part here is a subtraction. So that's going to be based on the smallest number of places past the decimal, which in this case will turn out to be 1, which is why we end up getting this as the answer. Does anybody have any questions about the calculation of delta G based on delta H and delta S? Okay. The next one here is delta G to K. Now, the equation that you're given here, and this is given at the end of the test, is delta G is negative RT ln of K. So we have to isolate K there. So we take the RT over the other side, so that's delta G naught over RT, or negative RT. And then in order to get K isolated, we have to take everything to the power of E. So E to the power of delta G over negative RT. So you can see everything gets plugged in there. And again, we're in this situation. We're given the value of R as being 8.314 joules per Kelvin per mole. The negative here is from this part here. So we need to convert this into joules, and we do that by doing 1,000 joules over 1 kilojoule. When we do this in our calculator, that should be an E down there, by the way, E to the power of that, and we end up getting 5.79 times 10 to the negative 11. There's no unit on K, so we don't include units. You'll notice all the units end up cancelling anyway. Does anybody have any questions about calculating K? Anybody have any questions about K? All right. Yeah.
For the units of K, it's just no units.
No units. You'll notice everything cancels. Do you see that?
Yeah.
The kilojoules cancel. The joules will cancel down here. The kelvins cancel here. The moles cancel here. You're left with nothing. It's dimensional.
And this is just equilibrium constant, right?
It is. Yeah. It's like that B over A I was talking about earlier. Yeah.
Yeah.
And R is always going to be negative 8.314, correct?
No, it's not negative. It's just 8.314. But the negative here comes from the fact it's negative RT ln K.
Yeah.
Okay. So the R value is 8.314 joules per Kelvin per mole. I think I give it in the questions on the test, but I'm not 100% sure that I do. If I don't, then I will add it in, but I think I do. I think I give it. Even if I don't give it, you would probably have it written down on your sheet of paper, I imagine.
Yeah.
All right, does anybody have any other questions about this so far? All right, let's look at the questions as they appear on the practice test, the ungraded copy, which of course will match exactly what you're going to see on the real one. Okay, let's have a look. So this is what it looks like, and you can see that it's just A's, B's, C's, D's, and E's, etc. The structure of this can vary. There could be 2 reactants and 3 products as well. That's another question that you could possibly be asked here, but it's done pretty much the same way. In order to get delta H, it's going to be 3 times D and plus 1 times E minus 2 times A, 3 times B, and 2 times C. So there's not even any red herrings here. You've got the units here to make sure you know what you're looking for. But if we're looking for enthalpy, that's delta H, and we're only interested in this column here. Does anybody have any questions about question 1 and how to do it?
So we use the actual coefficients for both.
Absolutely,
for both
yeah.
That's right.
Yeah, because the formula is the sum of the heats of formation. If you have 2 moles of something, you have to take that into account, which means it's going to be that plus whatever, same thing twice. So 2A is A plus A.
Right.
3B is B plus B plus B, and 2C is C plus C. Then you're adding all of that together.
Okay.
Now this one here is about entropy, and we're interested in S naught. We're only interested in this column. But again, it's the same deal. Anybody got any questions?
Actually, so is whenever we have to find delta S, I mean, when do we use that?
That's entropy. Delta S is entropy.
Right.
I'm sorry, what's your question exactly?
I mean, like, when do we use it for calculations?
Well, when you're looking for entropy.
Okay.
But we won't use delta S until we won't actually use the delta S value until we're looking at Gibbs free energy, which is the next one. So here it is. So Gibbs free energy, what you'll have to do is pretty much what you did in questions 1 and 2. You'll have to figure out delta H, and then you'll have to figure out delta S, and then apply delta G equals delta H minus T delta S. Using that same method as I showed you here, making sure that you do the unit conversion that allows you to match the kilojoules per mole and the kilojoules per mole. I think it does ask you to calculate in kilojoules per mole. So that's a good reminder to make sure you're doing what you need to be doing.
Right. So delta G degree was equal to delta H.
Delta G naught is how you pronounce it, Adam. What was that?
You said Enor?
Delta G naught is what you say, naught for the 0.
Naught.
Yeah, naught.
So delta G naught equals delta H naught minus S naught.
T delta S naught.
C delta S naught. All right.
Yeah, the T is the Kelvin temperature. You're given the temperature here, see 25 degrees Celsius, but you've got to convert that into kelvins.
Okay.
All right, but you're just applying that. As you can imagine, just practicing these will be good. All right, it's not hard. None of this is particularly difficult.
Right.
The last one here, I do give the R value. So was it Miriam? Were you asking about the R value? It is given to you here.
Yeah. Okay.
But I want you to look here. You're not after K. Look what you're after.
PK.
PK. So that's once you get K, you need to take the negative log of it. So the way you'll get K is using this formula here. Delta G is negative RT ln K. So K is going to be either the power of delta G naught over negative RT. So you will have to find delta G first, and then find K, and then take the negative log of that, and that will be your answer down here. Does anybody have any questions about the K calculation? Now keep in mind, remember, I do have videos for every single last one of these problems in this practice quiz. Every single last one. So that's where you would know that you would need to find the negative log of K at the end in order to get the answer. But again, practice, 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 and you'll be fine with this. Does anybody have any questions about 1 through 4?
No, not necessarily about that, but the real test is only going to be 10 questions this time?
Yeah, 12 actually, I think. Or 11. Or let's see, here we go. Let's see. No, 10. No, you're right. 10. You're right. 10. Yeah, only 10. It's a little bit less involved than test 2. Now, if you, I remember, I am allowing you here to use your handheld calculator during this test. But if you want to use the on-lot calculator and you want to practice with it, I have put a link in here so you can access it. There it is. All right. You could pull that out, put it to the side, arrange the screen if you want to. That's up to you. All right. But like I said, you can use your regular calculator for this test. I've done that. It's mostly out of convenience. The on-lot calculator usually works fine, Rebecca, right? Usually.
Or not.
Or not.
Maybe you can just do like from number 8 over and nobody can fix it.
Yeah. All right. Okay. Let's have a look at, does anybody have any other questions about 1 through 4? Anything at all? I don't think it's too bad. I really don't. I think if you practice these, you'll find that they're not too difficult. All right, let's move on to something a little bit more difficult. Well, it's not really difficult. It's just a little bit conceptually difficult. Once you get the hang of this, again, it's not too bad. So what I do is I give you a reaction. And the whole point of this is more to really focus in on, it's two things here, really. It's the nature of the heat of the heat reaction, or delta H, and on entropy, but mostly about entropy, really. And as I was saying earlier, the delta S is going to be, let me put up the equation for this. Delta S naught is the sum of the entropies of the products minus the sum of the entropies of the reactants. So in other words, read that as disorder of the products minus disorder of the reactants. And that's what entropy is. It's a measure of disorder. And what we know is that there's a hierarchy of order that can be gleaned from looking at the states of things. And here's what we know. We know that gases are better than aqueous ions, are better than pure liquids, and that's better than solids when we're talking about disorder. I think that makes a lot of sense. I mean, if you look at gases, you know, they're flying around and they're not bound by anything, really. I mean, except the container that they're in. Aqueous ions are going to be lots of aqueous ions dissolved in a pure liquid like water, and that's going to be more disorder than just pure liquid, which would be like pure water or pure bromine or something like that. And of course, solids are highly ordered. So, you know, you don't expect a great deal of order out of solids. So what it means is that when you're looking at an equation like this, you can look at the states of things and be able to determine or get an idea of the amount of disorder on each side. Now, what I can tell you is when I'm looking at this specific equation that we have here in this example, you'll notice on the reactant side, we have a solid and aqueous, just looking at the states by themselves. And on the other side, we've got two aqueous ions, or two sets of aqueous ions. I could tell immediately looking at that, there's more disorder on the product side than there is the reactant side. So it makes sense that we're going to get a positive value for delta S, because this is going to be a big number and this is going to be a small number. I immediately know that just by looking at it. I can be a little bit more quantitative about it though, by looking at the specific number of ions present on each side of the equation. It allows me to get an idea of the extent of the difference in disorder from going from the reactants to the products. So what I can just say is, well, the solid really isn't going to matter as far as disorder goes, because it's two ordered. All that's really going to matter is the sheer number of aqueous ions. And if you've got H2SO4, it splits into two H's and SO4. Now, I'm not really that interested in charges here. I just need to know how it splits up. And if there's three molecules of that, it's like there's three boxes of that. Consider it like 3 boxes of 2 apples and a banana, or a banana, whatever you want to say. So that would mean there's a total of 9 ions on the reactant side. And on the product side, we have 3 C2SO4, so that would be 9, and then 2 H3PO4s, that would be 8. 9 and 8 is 17. So we have 9 ions on the reactant side and then 17 ions on the product side. So that's more proof there that there's more disorder on the product side than there is the reactant side, which is why we're expecting a positive value for delta S. Does anybody have any questions about A there, part A?
So you didn't just take the actual numbers of coefficients, but you multiplied them by each element in the
Or each
the
component.
numbers you were just getting. I didn't see where you got those.
From each component, yeah. I mean, if you've got H3PO4, it actually splits into 4 total ions. You got 3 H's and a PO4. But then you got 2 sets of that, so that's 2 times 4 is 8.
Okay, and then you're counting each individual part.
That's right.
Okay, all right, thank you.
And the reason for that is because that's what it splits into, Rebecca. When you put it in water as aqueous ion, that's the number of particles it splits into. So this number of particles gives us a little bit of a measure, something we can look at to determine how much more disorder there is on one side than the other. Is that okay?
Yes, yes. I was actually just looking at the straight coefficients, so I was maybe saying 5 to 3.
Yeah, right.
You know, 5 on the product side, 3 on the reactant side, but it's actually more involved than that.
A little bit, yeah.
Okay.
Yeah, you can get a rough idea by looking at that, but it's not going to tell you the whole story.
Right. Okay. So we really need to break it down. I see that. Okay.
Yeah. Are you okay with the breaking down part?
Yes.
Yeah. Sometimes breaking up's hard to do, Rebecca. Just know that.
It is. You have, for me, I have to ignore the coefficients and do that one molecule and then repeat it.
Yeah. All right. So if you, I'll talk about the actual test question in a minute that relates to this, but we'll get to that. You'll have to do something similar there as well, but I'll show you exactly what you need to do for that in a second.
So like since the disorder is going to be a negative value, I mean
positive. No, it's positive. Because there's more
products minus reactants, right?
Yeah, there's more disorder on the product side than the reactant side.
Right.
So that means it's going to be a positive value for delta S.
And does that like tell us anything about what the heat of the reaction is going to be, whether it's exothermic or endothermic?
No, it has no link at all whatsoever. The only way that you'll know is to look at the reaction itself up here and read this name here. It's going to say exothermic or endothermic. All right, but it's not going to have any link to what's down here in the delta S. But it's a good question, Adam. I don't mean to sound flippant, but that's how you'll know.
Right.
So if it's exothermic, really, it becomes pretty easy at that point. It's exothermic. It means delta H is negative.
Exothermic was whenever heat is on the reactant side.
Product side.
Product side. All right.
Take a look. Take a look. I'll do these two energy diagrams here.
All right.
These are kind of important. I like them as examples here. But this one's exo, and this one's endo. Yeah, exo is always going to look like this. Reactants, and that's products. And remember that it's always products minus reactants for delta H. And for endo, it looks like this. Delta H is still P minus R. But look at the two here. For exo, you'll see that the products are lower than the reactants. So it's a small number minus a big number, which is why it comes out to be negative. And here, it's a big number minus a small number, which is why it comes out to be positive. That should be helpful to you. So you with me so far?
Absolutely.
That's good. That's good. Now, further, along with that, as a consequence of knowing these signs for delta H and delta S, we can actually get an idea of what's going on with delta G. Now, if you watch the video that goes along with this, I don't really feel like there's something you have to memorize or even something you have to actually put down on your sheet of paper, but I'm sure some people will, and that's fine, but I don't think it's really necessary. But I've got this this graphic. It's like a Cartesian plane type situation, and on one axis I've got delta S, and on the other axis I've got delta H, like this. And what we know is that, I can't remember if I've got them mixed. I might have them the other way around. I don't know. It doesn't really matter. But the whole point is that this is when delta H is positive and delta S is positive. This would be when delta H is positive and delta S is negative. And we've got these four different quadrants. The situation we have here is that delta S is positive and delta H is negative. Now, I know delta S is positive because I know that there's more disorder on the product side than the reactant side. And I know delta H is negative because it says the word exothermic next to the reaction. Is everybody clear on that? All right, now the equation that's in play here is delta G equals delta H minus T delta S. And delta H is a negative value. And T delta S, that's T times a positive value. Now T in and of itself is always going to be positive. There's no question about that. Every single time, T is going to be positive because T is in Kelvin. And Kelvin is always a positive value. It's impossible to have a negative Kelvin temperature. So what I would want you to see there is if you have a negative value and you're subtracting a positive value, it will always be negative. Which means that the reaction will always be spontaneous. And that's going to be the upshot of it. So if you look at the video, you'll see this quadrant thing, and it will tell you exactly what goes on in every single case. I think it's better to know from a looking at it kind of point of view what's going to happen. Does anybody have any questions about this specific one? All right, let me give you another example. You see, when the signs of delta S and delta H are opposite, when one's negative and one's positive, it's a little bit easier because it's either going to be spontaneous all the time or not spontaneous all the time. It's when they're the same sign that things begin to get a little bit more complicated. So let me do an example here. let me do an example where they are the same sign. And what I'll do is I'll make them both positive, just for kicks. Now, it's not the case here, but this is how it works. So delta G equals delta H minus T delta S. Delta H is a positive value. And T times, again, a positive value. So in this instance, what I would want you to see, and this is a little bit harder to see than what I was just talking about. If T is a very small value, then delta G will be positive. But if T is a high value, then delta G is going to be negative. Well, what I'm saying is there's going to be a value of T. I mean, the delta G is going to depend on the value of T, the sign of it. It's going to depend on T. If T is small, small t equals positive delta G, non-spontaneous. Big T equals a negative delta G, and the reaction will be spontaneous. The bottom line here is that whenever you've got the same sign on delta H and delta S, there's always going to be variation with temperature. And when they're a different sign, there's going to be no variation with temperature.
So what you wrote for the small t underneath valence electron and the delta G, what does that say?
Oh, no, it's positive. Plus VE, positive. Positive. Right. That's all it means. Positive.
But underneath that, that's like
non-spontaneous.
Oh, non-spontaneous.
Yeah. And if it's a big temperature, it's going to be negative delta G, and it's going to be a spontaneous process. Spontaneous in this context means it happens by itself without outside interference. And reactions that are spontaneous in one direction tend to be non-spontaneous in the opposite direction. All right, does anybody have any questions about that? About 2B? All right, let's take a look at the practice test here, and you'll see what kinds of questions you're going to be asked about this. So for question 5 here, what it says is, for the reaction below, determine the difference in relevant particles but allow for the determination of the sign of delta S. It sounds like a weird question, doesn't it? But really what you're doing is pretty much what we just did. It's pretty much what we just did in that test question. All right, let's take a squiz at it. So what I would want you to see is that on the reactant side, we have the solid, which you'll ignore. And then we have the particles on the products, on the reactant side. Does anybody want to tell me how many particles they see, aqueous ions, on the reactant side? Rebecca, I'll put you on the spot since you asked about it earlier. How many particles do you see?
Okay, when you say particles, are you talking about breaking it down? Or
Yes, breaking it down. That's right.
Okay.
Break it down, Rebecca.
And you're on the product side, correct?
Reactant side. Reactants. Let's look at the reactants first.
Reactants. Okay, so in that case, I see.
Remember, ignore the solid. Just look at the aqueous ions, right?
I see 6 LIs. I'm sorry, 1 LI for every 4 CLOs.
No.
Is that correct?
Nope.
Oh, I'm sorry. 1 LI, 1 CL, and 4 Os. No.
No.
Oh, that's one product. I'm glad you asked me because I'm getting it all wrong. All right, so there's 2 ions there.
Yeah.
And so there's 6 of them, so there must be 12.
12 is correct.
Okay, on the reactant side.
Yeah. So this is the thing. If it's a if it's a polyatomic ion, when you got two things here, that's only going to be one particle. How would you know there was more than one of those?
The parentheses.
Yeah, the parentheses, and you can see that on the other side here. We know that that's one Fe and three separate ClO4s.
Okay.
Whereas if it was something like FeBr3, you know that that's going to be one Fe and three Brs. But the difference, of course, there is that the Br is a single element, not a polyatomic ion.
Okay.
Is that fair enough?
Oh, yeah. Thank you.
Okay. Well, thank you for being brave. I appreciate it. We've got 12. We've got 12. Does anybody else want to take a guess at the product side? How many total ions we have on the product side?
Sure.
What do you think, Adam?
Yep. 2 iron and then 6 of the chlorate or chlorite. Chlorate.
Perchlorate. But anyway, yeah. Okay, so how many total? How many total?
2 plus 6, 8.
Yep. And what about the other one?
And 6 lithium and then 3 of the carbonate.
Mm-hmm.
So 6 plus 3, 9, and so that would be 17 overall.
Yep, that's great. That's wonderful. There we go. Right, now remember that delta S is going to be the sum of the S naughts of the products minus the sum of the S naught of the reactants. So it's almost like you can do 17 minus 12, which comes out to be plus 5. So that's the difference. That's the answer we're looking for. That's what we put, is plus 5.
So solids will be the only ones that we ignore, correct? Like everything.
Well,
else
yeah,
is-
absolutely, because if we're talking about entropy, the solid is not really going to affect the overall entropy of anything because solids are so ordered. Any disorder in the reaction is going to be the result of aqueous ions and how they break up in solution. The solids just don't do that.
And if we had liquids, we'd count those in too, right?
Well, that's the thing. I mean, I can tell you for a fact that the only things you're going to have to worry about in this question are solids and aqueous ions, but I wouldn't even count the liquids either.
All right.
If I had aqueous ions present, I would just look at the aqueous ions because they're the things that have the most entropy.
Okay. Thank you.
All right. Does anybody else have any questions about number 5? It takes a little getting used to, but again, if you practice it, it's not that bad. It really isn't. Any questions? Well, my advice would be draw a picture. And if this is something that bothers you, splitting things up into ions, can anybody give me an idea of what you should do if you have trouble splitting things up into ions? Is there a resource that you could perhaps go to practice? And what would that resource be?
My courses.
No, something a bit easier, Adam, something more specific.
Math.
No. If you have trouble splitting into ions, where should you go?
All
right. I'll tell you.
The molecule.
No, practice test 2. We did it in practice test 2. I included 4 questions where you had to split things into ions, right?
Right.
Yeah. Practice that puppy, right? Yeah. All right. How soon we forget. All right. Does anybody else have any questions about number 5? Anything about number 5? All right. Now, number 6. You're doing something similar there, except in this case, you're just really trying to determine the signs of delta S and the signs of delta H, which you can figure out. Delta H you get from here, whether it's exothermic or endothermic. And the delta S, you'll look at the number of particles on each side, and you'll say, well, which side has more particles? If there's more particles on the product side, then we know that delta S is positive. If we have more particles on the reactant side, we would know that delta S is negative. That's where it comes down to. Then we can determine the relationship between spontaneity and temperature. And that's that. I went through that earlier. Well, I'll do this one as an example though, just for kicks. So what I would do is I'd look at this, I'd say, well, I know what delta H is. Delta H is exothermic, so delta H is negative. I know that from the outset. And then I look at the particles and I see that there are, I don't actually have to do this, but I say there's 4 particles on the reactant side, aqueous ions. And then on the product side, I see 7. So I know there's more particles on the product side than the reactant side. And what that enables me to do is say that delta S is positive.
Mm-hmm.
And then I apply my equation. But I think realistically, people will just probably have it written down on a sheet of paper, which is why I'm not that fond of having a sheet of paper. But anyway, it's kind of like a crutch that's not really needed here. And we've got, see, negative, minus a negative. Sorry, minus a positive, I'm sorry. Which is going to be always negative. Which means it's always spontaneous. And that would be the answer. The reaction is spontaneous at all temperatures would be the answer. Does anybody have any questions? Anybody have any questions about that? Question 6.
My question is a technical question.
Mm-hmm.
Is there any playback coming from my laptop?
No.
Okay, perfect.
I did have a question,
Yeah,
and
Rebecca.
it may or may not be relevant. I understand the principles behind it, but it seems like a big assumption that the answer will always be negative. I mean, couldn't the positive? Oh no, because you're adding a negative. Never mind.
Yeah.
I thought there was one where.
Well, no, that's true when they're the same sign, Rebecca.
Okay.
Yeah, then there can be variation. It's exactly what you said, but not in this instance.
Okay, the different signs. Got it. Okay.
Yeah.
Mm-hmm.
I think that's handy to sort of use as a guide as well. Just look at the signs. Are they the same? Are they different? If they're different, there's going to be no variation with temperature. And if they're the same, there will be. So you're kind of doing a 50-50
Right.
thing at that point,
Mm-hmm.
and it becomes a little bit easier.
Okay.
All right, so I have a fun question. So whenever we go back to like just the disorder part of it, how gas is greater than aqueous, liquid, and then solid.
Mm-hmm.
Is there like any amplification within those, or is that like a higher course of chemistry?
I don't know. It might be some exceptions, I suppose, but in general, that's pretty much the way it goes.
All right.
Yeah, and yeah, I guess it would be something that's beyond the scope of what we're doing here.
Right.
All right. Any other questions about that? Okay, I think in my Zoom session, I said that we would get on to non-standard cells here as well. So I think we'll look into that. Now, there's a lot of background that goes along with this specific kind of problem, and a lot of stuff that goes into here. I don't know how many people have done anything to do with this at this point. Can somebody, did I say I was going to do this? I think I did in the Zoom session. I'd have to go back to the...
According to the table of contents, yes, you went all the way through the stoichiometry.
Oh, all the way through, yeah, okay, all right.
Yeah,
So
the first part.
Okay, okay, I'll do a little bit of background here just to just to sort of give you a little bit of go on this one. All right, so the situation is that we've got a cell. And the cell, in this instance, you can look at the cell diagram and you can see, actually, a little, something else here as well. Salt bridge. There we go. Okay.
That's the negative, eh? Like this is a battery, right?
It is. It is. It's a battery. That's right. And when we're looking at this business here, this double line here sort of separates the cells. And what we've got here is an electrode, which is going to be the X solid. And in that, we've got a solution of, in this case, it's X5+. So those are ions in solution there along with the X. On the other side, we've got, well, it's unlikely that the manganese dioxide is going to be a particularly good thing here. It's probably platinum. I'll say it's PT. In which case that gets ignored because the platinum is just becomes a way for us to be able to transfer electrons out of solution that doesn't have anything that conducts electricity in there. So we've got MnO2, we've got MnO4-. I probably should have platinum in the question, but it really gets ignored anyway, and H+. But that's the situation that we have, and that's the important thing to realize is the different parts of the cell here. Now, what we also know is that the cell produces a certain voltage that can be measured by a voltmeter, and that voltage is due to electrons that run through this wire. It's how batteries do electrical work. It's they produce electrons that can be run through something to produce power. It's how any of your battery-operated devices work. Does anybody have any questions so far? So what we can do? Sorry, do you have a question, Adam? Okay. So what we can do is we can catch the voltages of these different, we call them half cells. The whole thing's called a full cell, but these are called half cells. And they each have half reactions that go on in there as well. And I can actually give you these reactions here. Or at least I do for the manganese side. For the other side, you have to work it out. But this is how it works on the other side. Let's see. The one that matters is going to be the one that has MnO4- and MnO2 and H+. So that's going to be the half reaction that goes along with that one. And now if you're doing the extra credit, you'll see you'll have to look up tables and things for this. I make it a little bit easier because I actually give you the stuff here.
So if we're looking at this as like a regular car battery, would like the left side of the photo be like the positive charge, and then the right side would be like the negative charge?
In this instance, let me make it right here. It's the anode would be on the left, and the cathode would be on the right. Oxidation occurs at the anode, and reduction occurs at the cathode. The cathode would be the positive pole, and the anode would be the negative pole of the battery.
Ah, okay. Cathode positive, reduction, and then anode oxidation and negative.
Yeah, they don't think so much about the negative and positives there. Just focus more on the reduction and oxidation, which we'll get to in a second. Now, the other half reaction over here, and we if we're looking, these are always presented as reductions from the outset. It's going to look like this. X5 plus 5 electrons gives X solid. Now these are called reduction potentials because the electrons are all on the same side. They're always on the left side. And in any tables you're looking at that involve these half reactions, they're always reductions. They're always given as reductions. But let's focus on that X5 plus 5 electrons gives X solid. Is everybody okay with that? How I come up with that? Okay. Now, by convention, when you're given a cell diagram that looks like this, by convention, this business over here on the left is always the anode, and that's always the cathode. And it's just by convention, anode, cathode. Now we know that oxidation is at the anode. And you can remember that easily. O and A, they're both vowels. And reduction occurs at the cathode. They're both R and C. And if you've got any situation like this, that's going to be a reduction where the electrons are on that side, on the left side, and when they're on the other side, that's an oxidation. And that's really all you need to know. But remember that any reactions you're given are always going to be they're always given in the guise of a reduction. They're always a reduction potential. And the reduction potential for X5 plus is 1.95 volts. And the reduction potential for the other one is 1.70 volts.
Wait, okay. Say that last part about the volts.
Well, those are the reduction potentials. They're given to you.
Oh.
Now, the thing with a battery is that they're both not reductions. One has to be an oxidation, one has to be a reduction. There has to be an anode, there has to be a cathode. But the way these cells are written is that the anode is always presented as being on the left side. Every single time. So what that means is, and this is the consequence of it. Let me move this over a bit. The consequence of that is that we'll always have to flip the first one to turn it into an oxidation because the anode is always on the left side. So the situation becomes this. X solid gives X5 plus 5 electrons. That turns it into an oxidation. But when we do that, we also have to reverse the sign. So it becomes minus 1.95 volts. The other one stays as a reduction, stays as it is. And that would be positive 1.70 volts. So you can see the situation now is that one where we have electrons on one side and electrons on the other. What this means is that the top one is giving electrons away and the other one's accepting them. And those electrons are the exact same electrons. But it's not even, as you can see there, it's different. Does anybody have any questions so far?
So the anodes are just going to have subtraction value of the volts, and then the cathode.
No, more correctly, Adam, it's going to have the opposite sign because that could be a negative sign initially. So it would flip to positive, but it's always the opposite sign of what it was because you flipped the reaction.
So flipped as in, like we flipped the anode to the products, or am I overthinking it?
No. Look
Oh, we flipped it. We flipped it. Okay. Yeah. Okay.
Okay. You clear on that?
Yeah. I get that.
All right. So you flip the reaction. You have to flip the sign.
Yeah.
Okay, on the voltage, which you're always given, of course. But you see, it's not balanced. You see how you got 5 electrons? It's like we've got 5 electrons, but the bottom one's accepting 3. So we have to somehow make it so the electrons are the same. And the way we do that is we do this. We take the reaction and we multiply this one by 3. And I'll take this bottom reaction and I'll multiply it by 5. So if I do that, this is what we end up with. No, this will make it clear as to why I did this. So it'll be 3x solid gives 3x5 plus 15 electrons. Now what's important here is this does not change the voltage. Now I go into this in the video as to why it doesn't change the voltage, but it doesn't. But you'll notice here now that the electrons are the same, which means we're giving away the same number of electrons as the other one's accepting. And again, the voltage won't change here either. No, that should be, sorry, 20 H2O, I'm sorry.
I only laughed because I hear your clock.
Oh, okay. It's a loud one, isn't it?
Right? Is it like a grandfather clock?
Actually, I'll show you. Kind of cool, actually. My wife and I read tarot. This is a tarot clock. There you go.
Nice.
All right. So, any other questions so far? Okay. You're all fine with this so far? Nobody has any questions? This isn't my party, it's yours. You can cry if you want to. No? Okay.
I mean, like, whenever you use the 3 and the 5, I mean, where does that really come in? It's just part of it?
Well, it's to make the electrons equal, Adam. See, we need the same number of electrons in the top and in the bottom.
So that's where the X5 plus moves over to the cathode, and then where's the 3? Oh, the electrons. Yeah.
Yeah, it's the electrons that are important here. So when we add this together, you'll see that the electrons cancel out. They're no longer part of it. And then I just put everything together here. So we'll have 3x solid plus 5 MnO4 minus plus 20H plus gives 3x5 plus 5 MnO2 solid plus 20H2O. And equally important here, let's see, that would be 0.25, to be minus 0.25 volts. And that would be the cell voltage. And what's important here is this is the cell voltage under standard conditions where they're all 1 molar solutions. But the cell we're dealing with is not under standard conditions. And that's what we're told, it's a non-standard cell. Now the negative here would indicate that this cell is not spontaneously working. If it was positive, then it would be working, but this one doesn't work. And it's because the cell value is negative under standard conditions. Okay, I'll stop here for a second. Does anybody have any questions? So you'll notice that there's an equation here. This happens to be what's called the E naught value, which is the cell voltage under standard conditions. And there's an equation here that allows us to figure out, oh, that's a mistake. That should be E cell. Sorry. That I'm going to have to fix that. But E cell is E naught cell minus 0.0592 divided by n times the log of Q. Now the 0.0592 is the combination of a whole bunch of constants all multiplied together. Don't worry about that so much. What does matter is what these other values are. Now the E naught cell value is what we calculated up here. It's minus 0.25 volts. Minus 0.0592 over n, which is 15, and the log of Q. We'll get to Q in a second.
Like n as in the 3 and 5 multiplied together, right?
It's actually the number of electrons transferred in the balanced equation, which is that, yes, 15. So it's whatever you had to make the electrons to make them balance out, is the way I look at it. Is that okay, Adam?
Yeah.
Now the Q here is the reaction quotient, which we're all familiar with. So it's going to be x5 plus to the power of 3 multiplied by, well, no, just x5 plus to the power of 3. And, you know, what we're looking for here, now, let me get this over here. I'll bring that back in a second. But if you look at it, we've got only certain things here have concentrations. And those are the only things that are going to be part of this Q expression. Anything that's a solid won't have a concentration associated with it. So only the stuff here is what's going to be included in the Q expression. So the other things that are in there, we've got x5 plus to the power of 3. The MnO2 is a solid, that's not included. The X is a solid, that's not included. The MnO4 minus has a concentration associated with it, and that's going to be to the power of 5. And then we've got the H plus, which is to the power of 20. Now, it's not a coincidence that when you look at that, you see we've only got concentration values for X5 plus, for MnO4 minus, and for H plus. So those are the only things that are going to be in the Q expression, which is always going to be products over reactants. And then it's just plug and chug at that point. So the X5 plus value is 1.08 to the power of 3. And then we've got the MnO4 minus, that's 1.99. That's to the power of 5. And the H plus is 1.05, and that's to the power of 20.
These molarity concentrations are already given, so yeah, okay.
Yeah, they're given in the question. So I'm just going to do some math here. I've got my calculator. 1.08 to the power of 3 divided by 1.99 to the power of 5. And then also divided by 1.05 to the power of 20. Now what I get for that is 0.0152 for Q.
And Q is it's a constant, but not at equilibrium. So
Right, yeah, it's the reaction not at equilibrium. Yeah, that's right. Yeah, once these things reach equilibrium, it's a dead battery. That's what happens when your battery dies. The whole thing reaches equilibrium. So it works. All right. So what we've got here though is log Q. So it's log of Q, and it's important it's log and not ln. Anyway, you can do the math on that, and you can come up with whatever you need to come up with the answer for E cell.
So what for the battery itself, would the Q be larger or less than the K?
That's a good question.
It'll eventually come up.
You know, I think you got me thinking here. I think you'd want it to be, you want it more on the reactant side, which makes sense because it's the things that are reacting that is going to do that. And once your reactants run out, you've run out of battery, right? So think of it that way, Adam. I think that's how I'd best put it.
Right.
So once you do the math, that's how you get the answer for that one. Does anybody have any questions? That's just the whole thing in a nutshell, really. Okay. Now the last one here that we'll talk about will be electrochemical stoichiometry. This is very similar to the test question. That's why I can go back to the test question for this one either. It's pretty much the same thing. But what we're looking at is a situation where we have a cell, but we're trying to electroplate. And the way we can electroplate something is by putting in a current into the cell. If you want more information about that, you can look at the video. I don't want to go into it here. I want to more focus on the mechanics of this particular calculation. So if you want to apply a silver plate to a spoon, for example, you're going to run a current into it, and we can actually figure out how much metal will be deposited by doing some math here. So what we're looking at is this equation here, and that is that the amount of hitting the blank here, current over time. Just trying to figure out how much I want to say here. Oh, sorry, current. Yeah, coulombs in charge, current times time. Which is amps or coulombs per second times time in seconds.
So current A for absorbance?
No, amps, amperes, amps. Yeah. Times time in seconds. That gives you coulombs. The other important piece of information, I think this is given, I do give it here, the Faraday constant, 96485 coulombs per mole. So 1 mole of electrons carries a charge of 96485 coulombs, and I give that there in that constant. You can see it here, the Faraday constant.
That's a 1 mole minus.
Yeah, coulombs per mole. Oh no, one mole of electrons.
Right. Okay.
Yeah, not mole. Yeah,
Right.
one mole of E minus. 1 mole E minus. We'll say that.
And for the C over F's, C as in concentration, right?
No, coulombs.
Coulombs.
Yeah, see, that's a measure of electrical charge.
I'll just put E minus on that.
So
And
yeah,
S as in just seconds, or that's the disorder?
seconds. So the way we do this is we've got hours. So we take 4.32 hours. We can convert that to seconds because we know there's 3,600 seconds in an hour. And we can multiply that by the current, which is 2.90 coulombs per second. So that gives us a number of coulombs. Then we can figure out how many moles of electrons that is, because it's going to be 1 mole of electrons is 96485 coulombs, and that goes on the bottom to cancel the coulombs. And then we also have here the reaction, which tells us that 4 moles of electrons produces 1 mole of X solid. And then we can figure out how many grams by multiplying that by the molecular weight. But again, I don't know. I think this kind of problem becomes incredibly, trivial. Because if you've got a sheet of paper in front of you, it's highly unlikely you won't have one of these examples on there. So it's going to make it pretty easy. Unfortunately. So, yeah, this is why I struggle. This is why I struggle with a sheet of paper, because I think here it's almost like, well, you don't even have to learn anything. You can just write that down and you don't even have to know what any of this means. And that frustrates me greatly. That a student can just look at that and say, no, I'm just going to write that down. I don't really care about what it means. But I really like people to watch the videos. So I don't know. This is why I struggle with a sheet of paper.
I mean, like at the end, you just like cancel out all the values and then you just get what you need.
Yes, that's right. But I think it's good to know what some of these things mean and why they are what they are, right? And just to give yourself a little background, watch the video.
Absolutely. Where would it be in the section of voltaic acid?
It's called Electrochemical Stoichiometry. There's a video for it in the mini lectures.
Electrochemical.
Right here, Adam.
Stoichiometry. It's just fun stuff.
Yeah, right here. Take a look. Right here.
All right.
Would the answer have 3 significant figures?
It would, in this instance, yes, because
Okay.
the 4.32 and the 2.90.
Okay, that's what I was thinking.
Does anybody have any other questions that they want to ask here?
When do we get into like like small batteries, like just say like the batteries inside like a Tesla car or whatever?
Oh, well, I mean, you know those essay questions?
Yeah.
Yeah, it's those are some of those are questions that relate to stuff like that. Not exactly what you just said, but at least you'll get some. you'll get some essence of what's going on in the battery.
It's like basically like liquid, not liquid, but like aqueous solutions inside, and then.
Oh no, it's more like in a dry cell battery. It's more like a paste. And you'll see this when you get into it, when you get into dry cell batteries. Yeah.
Huh. Okay.
All right. Does anybody have any other questions that they want to ask about any of the stuff we've been through today? Questions 1 through 8 on the test. Well, obviously what that means is that we'll be handling the other questions on next Tuesday's Zoom session. They're not that difficult, but you do have to practice them. And I know you'll have questions for me on those next time, but I don't want to get into them now.
I actually have one question that's not relevant towards the 8. It's more towards the clock.
Yes.
What's a tarot?
Tarot, it's a T-A-R-O-T. It's a
tarot, like a tarot. Tarot.
Tarot, yes. They're cards, right? You read them for various purposes.
Right. So, like those. So, those numbers, were they Roman numerals?
There were numbers on the cards. They were Roman numerals.
Oh, I gotta look that one up.
Yeah, look it up.
Yeah.
All right. We can talk about it privately later if you'd like. It's probably not appropriate.
Oh, yeah, absolutely.
Zoom session. All right. Does anybody have any other questions? Gypsy Insights by Michelle. That's the YouTube channel, if you're interested.
What is it?
Gypsy Insights by Michelle. If you're interested in looking at some tarot.
What is it called? Gypsy.
I've written it down here. It's on YouTube. You see it?
Oh, Gypsy Insights.
Yeah. All right, we'll leave it there for today unless anybody's got any other questions. Anybody got any other questions?
No, sir.
Okay. All right. Well, I'll see you all next time. Hey. All right. If you got any questions, let me know.
Okay, thank you.
Thank you. Bye-bye.
See you in 30 minutes, sir.
Have a good day.
Yeah. See you in 30.